Good evening and welcome to the Light Lab. It is lovely to have you here. Tonight we are looking at an experiment so simple that it can be drawn in seconds, yet so strange that physicists still disagree about what it means. This is the quantum experiment that broke reality. Before we begin, I would love to know where in the world you're watching from tonight. Perhaps you're in a quiet bedroom, resting on the sofa, or listening somewhere a little farther from home. Wherever you are, I hope you're comfortable, settled, and ready to slowly unwind. If you enjoy these relaxing explorations and would like to hear more, leaving a like and subscribing really helps this sleepy little channel continue to grow. And to everyone who has already subscribed, thank you. Your support genuinely means a great deal. I will try not to make tonight's experiment quite interesting enough to keep you awake. Although an experiment involving particles, waves, two narrow slits, and the apparent disappearance of reality as we normally understand it, may make that slightly difficult. So, let us begin. How can a single particle pass through an experiment one at a time, arrive at one definite point, and still behave as though it somehow encountered two different paths? At first glance, the double-slit experiment hardly looks capable of causing trouble. The arrangement is almost embarrassingly simple. There is a source that sends out light or particles, a barrier containing two narrow openings, and a screen that records where each arrival lands. No enormous machine, no distant galaxy. Just a source, two slits, and a surface waiting quietly on the other side. If we approach the experiment using ordinary experience, the answer seems obvious. Imagine firing tiny pellets towards the barrier. Each pellet would pass through the left opening or the right opening. It would follow one continuous route through space, strike the screen, and leave a mark. After many pellets had been fired, two broad clusters would form behind the two openings. This is the sort of behavior classical physics encourages us to expect. A grain of sand does not divide its journey between two doorways. Familiar objects appear to occupy definite places and travel along definite paths, whether or not anyone happens to be watching them. Light makes the experiment more interesting. When coherent light passes through both slits, the screen does not simply show two bright bands. Instead, it reveals an interference pattern made from alternating bright and dark regions. The contributions from the two openings combine. In some places, they reinforce one another, producing greater intensity. In other places, they cancel, producing darkness. That is recognizably wave behavior. Water waves can overlap and form similar regions of reinforcement and cancellation. So when light creates an interference pattern, it seems natural to imagine waves spreading through both openings and overlapping beyond the barrier. The deeper difficulty appears when the experiment is performed with objects normally called particles. Electrons can be sent towards the slits. So can atoms, neutrons, and even large molecules under carefully controlled conditions. When the experiment preserves coherence and prevents the surrounding environment from revealing which path was taken, the same basic pattern appears. Alternating regions of high and low detection probability gradually form across the screen, yet each arrival is localized. An electron does not appear as a faint mist spread across the entire pattern. It produces one small detection event at one particular place. The next electron produces another point elsewhere. At first the marks seem scattered and irregular, but as more electrons arrive, the interference pattern slowly emerges from those individual impacts. Each event looks like the arrival of a particle, but the final distribution depends on interference normally associated with waves. Even more remarkably, the electrons can be released one at a time, with enough separation that only one electron is travelling through the apparatus at any given moment. The pattern still builds. There is no need for one electron to collide with another and arrange the fringes collectively. Each electron contributes a single point, while the probability of where that point appears is governed by an arrangement containing two available paths. Richard Feynman regarded two-path interference as containing the central mystery of quantum mechanics. The reason was not that the mathematics failed. It works extremely well. The difficulty lies in forming a simple physical story that matches what the calculation predicts. With both slits open and no reliable path information available, interference appears. If a detector is introduced that can distinguish the left path from the right path, the interference disappears. The screen then shows a distribution resembling two overlapping single-slit patterns. Remove the path distinction, and interference can return. This is the heart of the puzzle. The behaviour changes according to whether the alternatives remain coherent and indistinguishable. It does not require a human observer staring intensely at the equipment. A detector does not need to be conscious or curious. It only needs to become physically correlated with the path strongly enough for the alternatives to be distinguished. The claim that the experiment broke reality is dramatic, but it should not be taken literally. Physical law does not collapse when the slits are opened. What breaks is a particular classical picture of reality. That picture says that a particle should possess a definite path independently of how the experiment is arranged, and that measurement merely reveals the route that was already there. The interference pattern shows that this assumption cannot be applied in the simple classical way. Treating every electron as an ordinary tiny object secretly choosing one slit, while the other becomes irrelevant, does not reproduce the observed distribution. Quantum mechanics replaces that classical story with the wave function. The wave function evolves according to precise mathematical rules and assigns probability amplitudes to possible outcomes. Those amplitudes can reinforce or cancel, producing the interference pattern. When a measurement yields path information or a final position, one definite result is recorded. But what exactly is the wave function? It might represent a real physical structure. It might describe possibilities rather than material substance. It might encode information about a system. It might guide hidden particle trajectories, as in Bohmian mechanics. It might describe branching realities, as in the many worlds interpretation. Or it might belong to a category for which everyday language has no perfect equivalent. The experiment gives remarkably clear predictions. It tells us what patterns will appear, when they will disappear, and how outcomes will be distributed. What it does not provide is one universally accepted picture of what happens between the source and the screen. And that is why two narrow openings continue to trouble our deepest assumptions about the world. To understand why the double-slit experiment became so unsettling, it helps to begin with a much older kind of interference. Long before electrons were sent through narrow openings one at a time, scientists were already asking a simpler question. Was light made from particles, or was it a wave? The disagreement reached back to the 17th century. Christian Huygens argued that light behaved as a wave spreading through space. In his picture, every point reached by a wave could act as the source of smaller secondary waves, and their combined motion determined how light travelled. This idea became known as Huygens' principle, and it offered a natural way to understand reflection and refraction. Isaac Newton preferred a different picture. He imagined light as a stream of tiny corpuscles or particles moving along definite paths. Newton's account matched the mechanical physics that had worked so well for falling objects, planets, and projectiles. If matter followed clear trajectories, perhaps light did too. Newton's reputation was enormous, and his corpuscular theory remained influential for generations. But light refused to behave quite like a collection of miniature pellets. At the beginning of the 19th century, the English physician and physicist Thomas Young carried out experiments that made the wave character of light difficult to ignore. Young allowed light to pass through two closely spaced openings and observed the pattern formed beyond them. If light consisted only of independent particles travelling through one opening or the other, the natural expectation would be two bright regions. Each opening would produce its own patch of illumination, and the two patches would overlap where they met. That was not what appeared. Instead, the light formed a sequence of bright and dark bands called interference fringes. Some regions received more light than either opening would have produced alone, while others became extremely dim, even though light from both openings could reach them. This is one of the defining signatures of waves. Imagine 2 points on a calm pond producing circular ripples. Where the crest of one ripple meets the crest of another, the disturbances reinforce each other and form a larger wave. Where a crest meets a trough, they oppose each other and may almost completely cancel. The first case is called constructive interference. The second is called destructive interference. Sound waves behave similarly. 2 sound waves with matching timing can reinforce one another, while waves that are out of step can reduce the resulting sound. Modern noise-cancelling headphones use this principle by producing sound designed to oppose unwanted noise. The world is rarely considerate enough to become completely silent, but it can at least be persuaded to quieten down. With light, the same idea depends on phase. Phase describes where a wave is within its repeating cycle. When light waves from the 2 openings arrive in step, they reinforce one another and the screen records a bright fringe. When they arrive sufficiently out of step, they cancel, and the recorded intensity falls. 2 overlapping beams therefore do not merely produce the sum of 2 separate brightness patterns. Their relative phase matters. In some places, the combined light is stronger. In others, the presence of the second contribution reduces the brightness. That point is especially important. Opening an additional route for light can make parts of the screen darker. If independent pellets were thrown through 2 openings, opening the second slit could add more impacts, but it could not create carefully arranged regions where impacts almost disappear. The pattern is sensitive to the design of the experiment. The wavelength of the light helps determine the spacing between the fringes. Longer wavelengths generally produce more widely separated bands, while shorter wavelengths produce more closely packed ones. The distance between the openings matters as well. Bringing the slits closer together tends to spread the pattern more widely across the screen. Increasing their separation brings the fringes closer together. Moving the screen farther from the barrier usually allows the pattern to spread over a larger area. Coherence is equally essential. For stable fringes to appear, the light reaching the openings must maintain a predictable phase relationship. If that relationship fluctuates randomly, the bands shift and wash into a smoother distribution. Modern experiments often use lasers because laser light can possess a high degree of coherence. Thomas Young did not have a laser. He used sunlight and arranged it so that a narrow opening first created a more controlled source before the light reached the 2 paths. Young's result gave wave theory something stronger than a vague resemblance. Interference offered a clear mechanism and a distinctive pattern. The bright fringes came from reinforcement. The dark fringes came from cancellation. The geometry of the apparatus determined where they appeared. During the 19th century, the wave description became even more powerful. Augustin Jean Fresnel developed a detailed theory of diffraction and interference. James Clerk Maxwell later showed that light could be understood as an electromagnetic wave formed from oscillating electric and magnetic fields travelling through space. By then, the argument seemed settled. Newton's corpuscles had been replaced by waves. Light reflected, refracted, diffracted, and interfered because it was an electromagnetic disturbance extending through space. The 2-slit pattern appeared to be one of the clearest demonstrations that this classical wave picture was correct. It explained why light could brighten one region and darken another, and it fitted naturally into the growing theory of electromagnetism. For a time, the mystery seemed settled. Light was a wave. The difficulty was that nature had not quite finished answering. By the middle of the 19th century, the wave theory of light seemed to have won. Thomas Young's interference experiments had shown that light could reinforce and cancel itself. Augustin Jean Fresnel had developed a much more complete theory of diffraction. Then James Clerk Maxwell brought electricity, magnetism, and light together within one mathematical framework. Maxwell showed that changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. Under the right conditions, these linked disturbances can travel through space as electromagnetic waves. When Maxwell calculated the speed of those waves, the result matched the measured speed of light. That was not a small coincidence. It suggested that visible light was itself an electromagnetic wave. The new theory was remarkably successful. Reflection could be understood as an electromagnetic wave responding to the boundary between different materials. Refraction followed from changes in the way the wave travelled through matter. Diffraction described the spreading of light around openings and edges. Interference followed from the superposition of overlapping waves. Polarization emerged because the electromagnetic field oscillations could be oriented in particular directions. Maxwell's theory also revealed that visible light belonged to a much wider family. Radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays and gamma rays are all forms of electromagnetic radiation. They differ mainly in wavelength and frequency rather than belonging to completely separate categories. Human eyes happen to detect only a narrow section of this enormous spectrum. For a while, the picture looked wonderfully complete. Light was an electromagnetic wave. Its behaviour could be calculated with extraordinary precision. The theory was elegant, unified, and useful. Unfortunately for classical physics, heat was quietly preparing a complaint. Physicists were studying the radiation emitted by hot objects. Any object with a temperature above absolute zero emits electromagnetic radiation. A warm surface gives off mostly infrared radiation. As an object becomes hotter, the amount of radiation increases and the dominant wavelengths shift. A sufficiently hot piece of metal begins to glow red, then orange, and eventually white. Scientists used an idealized object called a black body to study this process. A perfect black body absorbs all electromagnetic radiation that reaches it and emits radiation with a spectrum determined only by its temperature. Classical theories could describe parts of this spectrum, but they failed badly at short wavelengths. According to the classical calculation, a hot object should emit an unlimited amount of energy at high frequencies. This absurd prediction became known as the ultraviolet catastrophe. Real ovens do not produce infinite ultraviolet radiation, which is fortunate for anyone standing nearby. In 1900, Max Planck found a mathematical solution. He proposed that the material producing the radiation could exchange energy only in discrete amounts. These units were called quanta. Planck introduced a constant of nature, now known as Planck's constant, connecting the size of an energy quantum to the frequency involved. The central relationship can be written in words as energy equals Planck's constant multiplied by frequency. Higher frequency radiation therefore corresponds to larger energy quanta. Lower frequency radiation corresponds to smaller ones. Planck initially treated quantization as a way of obtaining the correct spectrum from matter interacting with radiation. He did not immediately claim that light itself always travelled through space as a collection of particles. Even so, the idea introduced a deep discontinuity into physics. Energy exchange was not always smooth. Under certain conditions, it occurred in distinct steps. Albert Einstein pushed this idea much further in 1905. Einstein was considering the photoelectric effect, in which light shining on a material can cause electrons to be released from its surface. Classical wave theory seemed to suggest that brighter light should deliver more energy, and therefore eventually release electrons, regardless of the light's frequency. The experiments did not behave that way. Below a certain threshold frequency, increasing the brightness did not release electrons. A brighter beam delivered more total light, but if each part of that light had too low a frequency, no electrons emerged. Above the threshold frequency, electrons could be released almost immediately, even when the light was faint. Increasing the frequency gave the emitted electrons more kinetic energy. Increasing the brightness mainly increased the number of electrons released, provided the frequency was already high enough. Einstein explained this by proposing that light transfers energy in localized packets. Each packet carries an amount determined by its frequency. These packets were later called photons. An electron in the material absorbs energy through one quantum event. If the photon's energy is below the amount needed to escape the material, the electron remains bound. Sending more low-energy photons does not usually allow one electron to collect their energy gradually in the simple classical manner. Each individual interaction remains insufficient. A higher frequency photon carries more energy. Once that energy exceeds the material's binding requirement, the electron can escape. Any remaining energy appears largely as the electron's kinetic energy. This was distinctly particle-like behavior. Energy arrived in localized, indivisible transfers rather than being spread continuously across the wavefront in the way classical electromagnetic theory seemed to imply. Yet light had not stopped producing interference. Young's fringes did not disappear. Diffraction did not become an illusion. Maxwell's equations did not suddenly become useless. This creates the temptation to say that light is a wave when it travels, and a particle when it arrives. That phrase can be helpful as a first approximation, but it is also too classical. A photon is not simply a miniature pellet hiding inside an ordinary electromagnetic wave. Nor is quantum light an ordinary material wave that merely condenses into a particle at the final moment. Quantum theory describes light through quantum states and electromagnetic fields. These states can produce interference because probability amplitudes associated with different alternatives combine. They also produce discrete detections because light exchanges energy and momentum with matter in quantized events. Both behaviors belong to the same quantum description. This becomes especially clear when photons are sent towards two slits one at a time. Each photon produces one complete detection event at one position on the screen. It does not leave half a photon in one place and the other half somewhere else. At first, the individual points appear random. As more photons arrive, however, the interference pattern gradually emerges. The distribution of those localized events depends on both available paths. The arrival is discrete, but the probabilities are shaped by interference. Light had therefore refused to remain only a classical wave. Yet it had not returned to Newton's simple stream of independent corpuscles either. It had become something more difficult to picture and far more powerful to calculate. Light had begun as the apparent wave, only to reveal that it could transfer energy in discrete packets. Louis de Broglie wondered whether the puzzle might work in the opposite direction. Matter had always seemed to belong on the particle side of the divide. An electron had mass, electric charge, and momentum. It could strike a detector at one definite point. It could be accelerated, deflected, and counted. These were all qualities associated with particles rather than waves. But if light, long understood as a wave, could display particle-like behavior, perhaps matter, long understood as particulate, could display wave-like behavior. In 1924, the French physicist Louis de Broglie proposed that every material particle has an associated wavelength. This was not limited to electrons. In principle, it applied to atoms, molecules, grains of dust, planets, and any other object carrying momentum. The relationship can be stated simply as wavelength equals Planck's constant divided by momentum. Momentum depends on both mass and motion. A heavier object generally has more momentum than a lighter one travelling at the same speed. A faster particle has more momentum than the same particle moving slowly. According to de Broglie's relationship, greater momentum corresponds to a shorter wavelength. This immediately explains why the wave character of matter is not obvious in daily life. Planck's constant is extraordinarily small. For an electron, which has a tiny mass, the associated wavelength can be large enough to become comparable with atomic structures or carefully manufactured openings. Under those conditions, diffraction and interference can be observed. For something such as a tennis ball, a cup, or a person walking across a room, the wavelength is incomprehensibly small. It is so far below the scale of atoms that no ordinary experiment could reveal a noticeable pattern. A person therefore does possess a de Broglie wavelength in the mathematical sense, although there is little danger of someone diffracting around the kitchen table. Slow particles can have longer wavelengths than fast ones because their momentum is smaller. Light particles can also have more noticeable wavelengths than heavy objects under comparable conditions. This does not mean that slower is always easier experimentally, since extremely slow particles may be difficult to control and can interact strongly with their surroundings. It simply reflects the inverse relationship between momentum and wavelength. De Broglie's proposal extended wave-particle duality beyond radiation. It suggested that wave behavior was not an unusual property belonging only to light. It might be a general feature of quantum objects. The word wave, however, needs to be handled carefully. An electron's wave character does not mean that the electron is a tiny solid sphere physically wriggling from side to side as it travels, nor does it mean that matter is made from an invisible liquid sloshing through space. Ordinary water waves involve the coordinated motion of water molecules. Sound waves involve compressions and expansions moving through a material. The wave associated with a quantum particle is not simply another example of that kind. De Broglie's original idea soon became part of a broader mathematical theory. Erwin Schrödinger developed his wave equation in the middle of the 1920s, providing a systematic description of how quantum states change over time. The Schrödinger equation plays a role in quantum mechanics, somewhat comparable to the role of Newton's laws in classical mechanics. Given a description of a quantum system and the forces acting upon it, the equation determines how its wave function evolves. The wave function can be spread across space. For an electron in an atom, it can occupy a region surrounding the atomic nucleus rather than tracing a miniature planetary orbit. For a freely moving electron, it may extend across a wide area. In a two-path experiment, it can contain contributions associated with more than one available route. The wave function does not directly tell us that a detectable piece of the electron is present everywhere it has a non-zero value. Instead, it encodes probability amplitudes. These amplitudes determine the probabilities of different outcomes when a measurement is made. They also carry phase. Phase is essential because amplitudes do not combine like ordinary probabilities. When two parts of a wave function overlap, their phases determine whether they reinforce or cancel. Contributions arriving in step can increase the probability of detection. Contributions arriving out of step can reduce it, sometimes almost to zero. This gives quantum mechanics its interference structure. Suppose an electron approaches a barrier containing two narrow slits. If its de Broglie wavelength is comparable with the relevant dimensions of the apparatus, the openings cannot be treated merely as two independent doorways for a classical particle. The electron's quantum state can diffract at each slit. Beyond the barrier, the path amplitudes overlap. Their relative phases vary across the detection screen, producing alternating regions where detection is more likely and less likely. The wavelength helps determine the scale of the pattern. If it is much smaller than the slit width and separation, wave effects may become difficult to distinguish, and the motion begins to resemble a classical trajectory. If the wavelength is comparable with the dimensions of the openings, diffraction becomes pronounced, and interference fringes can spread clearly across the screen. This is why the geometry must be matched carefully to the particles being used. Visible light has wavelengths measuring hundreds of billionths of a meter. Electron wavelengths can be much shorter, depending on their momentum, so electron experiments may require slits, crystals, or other structures separated on microscopic or atomic scales. De Broglie had transformed the question. Matter was no longer confined to the classical image of compact objects moving along definite paths. Its behavior could depend on wavelength, phase, diffraction, and interference. Yet the particle-like features remained. An electron still arrived at one localized point. It still carried its full electric charge. It did not spread its final impact evenly across the screen. The emerging quantum picture therefore did not replace particles with ordinary waves. It joined localized detection with spatially extended probability amplitudes. For the double-slit experiment, this made a remarkable prediction. Electrons should be capable of forming an interference pattern, not because many electrons push and pull one another into bands, but because the quantum state associated with each electron can develop through both available paths. The idea sounded bold. It also offered a direct experimental test. If matter really possessed a wavelength, then electrons should diffract and interfere, and before long they did. Louis de Broglie's proposal was elegant, but elegance alone does not make a theory true. If electrons really possessed a wavelength, that wave behaviour had to appear in experiments. The first decisive evidence arrived only a few years later. At Bell Telephone Laboratories in the United States, Clinton Davison and Lester Germer were studying how electrons scattered from the surface of a nickel crystal. Their original purpose was not to confirm matter waves. They were investigating the behaviour of electron beams and the structure of materials. The apparatus fired electrons towards a carefully prepared nickel target. A movable detector then measured how many electrons emerged at different angles after interacting with the crystal. If electrons behaved only as tiny classical particles, their distribution should have been governed mainly by collisions with individual atoms. Some electrons might bounce away in one direction and others in another, producing a relatively smooth pattern determined by the geometry and energy of the impacts. Instead, Davison and Germer observed pronounced peaks at particular angles. Large numbers of electrons appeared in certain directions, while comparatively few appeared between them. This was the familiar signature of diffraction. Diffraction occurs when waves encounter openings, edges, or repeating structures whose dimensions are comparable with their wavelength. The waves spread, overlap, and interfere. At some angles, the contributions reinforce one another. At others, they cancel. A crystal is especially useful for revealing this behaviour because it is not a random collection of atoms. Its atoms are arranged in a regular repeating structure. Layer after layer follows an ordered pattern, with separations often measured in tenths of a billionth of a metre. That repeating atomic structure can act like an extremely fine diffraction grating. When an electron wave interacts with different atomic layers, the scattered contributions travel slightly different distances. At certain angles, those path differences correspond to whole numbers of wavelengths. The contributions then arrive in phase and reinforce one another, producing a strong intensity peak. At other angles, the contributions arrive out of phase and largely cancel. The detector records fewer electrons there. This principle was already familiar from X-ray diffraction. X-rays possess wavelengths similar to the spacing between atoms in crystals, allowing them to reveal internal crystal structures through distinct diffraction patterns. Davison and Germer found that electrons could behave in much the same way. The crucial test involved comparing the measured pattern with de Broglie's prediction. The electron's momentum could be calculated from the voltage used to accelerate them. De Broglie's relationship then assigned them a wavelength. According to wavelength equals Planck's constant divided by momentum. The wavelength inferred from the diffraction peaks closely matched the wavelength predicted from the electron's momentum. This was not merely a loose visual similarity to wave behaviour. The quantitative agreement was the important part. The location of the peaks followed the geometry expected for waves of the predicted wavelength interacting with the known spacing of the nickel crystal. Matter waves had become measurable. At around the same time, the British physicist George Paget Thomson carried out an independent series of experiments. Rather than scattering electrons from the surface of a crystal, Thomson sent a beam of fast electrons through very thin sheets of material. Beyond the material, the electrons formed rings on a photographic plate. These rings were diffraction patterns. Electrons passing through different parts of the crystal structure produced overlapping amplitudes that reinforced at particular angles. Because the thin material contained many tiny crystalline regions with different orientations, the preferred diffraction directions appeared as circular rings rather than isolated spots. The historical detail was difficult to resist. George Paget Thomson's father, Joseph John Thomson, had played a central role in establishing the electron as a particle near the end of the 19th century. His experiments had shown that cathode rays consisted of negatively charged entities much smaller than atoms. The sun then helped demonstrate that those same electrons also possessed wave behaviour. Physics had managed to turn one family into a particularly efficient argument with itself. There was no genuine contradiction between the two experiments. Joseph John Thomson had shown that electrons carried definite charge and responded as identifiable particles. George Paget Thomson showed that their distribution through matter depended on wavelength, phase, diffraction, and interference. Both sets of evidence were real. Neither could simply be discarded. In 1937, Clinton Davison and George Paget Thomson shared the Nobel Prize in Physics for the experimental discovery of electron diffraction. Lester Germer's contribution to the Bell Telephone Laboratory's work remained scientifically important, even though he was not included in the prize. The experiments confirmed de Broglie's central claim. Electrons could not be represented completely as tiny Newtonian objects following only sharply defined paths through space. A classical particle might scatter from atoms, but it would not naturally produce a diffraction pattern whose peaks were determined by a wavelength calculated from its momentum. The observed distribution required phase relationships between different possible scattering paths. This did not mean that electrons had ceased to be detectable as particles. Each electron still delivered its charge and energy in one local interaction. A photographic plate darkened through individual events. A detector registered separate arrivals. The wave behavior appeared in the pattern formed by many such arrivals. At first, it was possible to imagine that this pattern resulted from the collective behavior of a large electron beam. Perhaps electrons travelling together influenced one another. Perhaps the wave-like distribution emerged only because many particles were present at the same time. That possibility raised a sharper question. What would happen if the beam were weakened until the electrons travelled through the apparatus separately? If only one electron were present at a time, there would be no neighbouring electron with which it could cooperate. Each arrival would occur alone. Would the diffraction pattern disappear, leaving only the ordinary scattering expected from individual particles? Or would the pattern continue to build point by point, even when every electron passed through the experiment in complete isolation? That was the test capable of turning matter wave diffraction into something far stranger. The most revealing version of electron interference begins by turning the source down. Instead of sending a strong beam containing enormous numbers of electrons, the experiment is arranged so that the particles are emitted slowly and detected separately. Each arrival appears as a single isolated point. There is no continuous glow and no smooth wave painted across the screen. One electron arrives, then another, then another. Each event is localized. The electron does not leave a faint trace spread across several regions. It does not divide its electric charge into smaller pieces and deposit a little behind each slit. The detector records one complete interaction at one particular position. At first, the pattern looks like nothing at all. The first few points appear scattered almost randomly. One electron lands near the center. Another appears farther to one side. A third arrives somewhere else. There is no visible order and no obvious clue that the collection will eventually reveal anything more interesting than a loose cloud of impacts. After a few dozen detections, the screen still looks irregular. Some places have received several electrons while nearby regions remain empty. But these differences could easily be dismissed as chance. As the number rises into the hundreds, faint structure begins to emerge. Certain bands receive more impacts than others. Regions with fewer detections appear between them. With thousands of electrons, the organization becomes unmistakable. Alternating areas of high and low detection probability stretch across the screen. After many thousands of arrivals, the complete interference pattern becomes clear. The important point is that no individual electron arrives as the pattern. Each electron contributes only one dot. The interference exists in the distribution of many independent detections. This behavior is often illustrated by photographs or recordings in which the screen gradually fills. At the beginning, there are only a few bright points against darkness. Later, those points gather into delicate bands. It is almost as though a hidden image has been developing one grain at a time. Experiments demonstrating electron interference developed over several decades. In the early 1960s, the German physicist Klaus Jonsson carried out a landmark experiment using electrons in extremely fine slits. The The required dimensions were tiny because the electron wavelengths involved were far shorter than the wavelengths of visible light. Jonssen's results clearly demonstrated electron interference using a multiple slit arrangement, including a two-slit configuration. The experiment showed that matter waves could be handled in a form closely resembling the famous optical experiment performed with light. Later, Akira Tonomura and his colleagues at Hitae produced some of the most striking visual demonstrations of the effect. Their work used an electron biprism rather than a simple barrier with two mechanically cut slits. An electron biprism creates two coherent electron paths using a very fine-charged filament and surrounding electrodes. The electric field gently redirects parts of the electron wave so that the two path contributions overlap. Where they overlap, their probability amplitudes interfere. Although the apparatus differs from a literal pair of openings, the essential physics is the same. There are two coherent alternatives, and their amplitudes combine to determine the detection distribution. Tonomura's team reduced the electron intensity until detections arrived individually. Their apparatus could be operated so that, on average, no more than one electron was travelling through the interference region at any moment. The separation between emissions was much longer than the time needed for one electron to pass through the equipment. By the time the next electron entered, the previous one had already reached the detector. This removes a tempting classical explanation. The fringes cannot be created through ordinary collisions or forces between simultaneous electrons, because the particles are not travelling together. There is no crowd of electrons quietly organising itself into brighter and darker lanes. Each electron passes through the experiment alone, yet every arrival contributes to the same final pattern. The first electron cannot know where later electrons will land. The final electron does not need to consult the earlier ones. Nothing in the experiment resembles a group of particles negotiating where the fringes should appear. Quantum mechanics instead assigns a wave function to each electron. Where the apparatus provides two coherent paths, the probability amplitudes associated with those paths overlap. Their phases determine where detection is more likely and where it is less likely. The resulting probability distribution remains the same from one run to another, provided the experimental conditions are preserved. The exact position of an individual electron is not predicted. Quantum mechanics may assign one region a greater probability than another, but it does not usually specify the precise point that the next electron must strike. This randomness is not the same as complete arbitrariness. An arbitrary process could produce almost any distribution. The electron experiment does not. Individual impacts vary unpredictably, but the accumulated pattern follows a precise mathematical structure. If the experiment is repeated under the same conditions, the exact sequence of dots will differ. The first electron may land in a different place, and so may the second. After sufficiently many events, however, the same interference fringes emerge. This is similar to repeated throws of an ordinary die only in a limited sense. No one can confidently predict the next result, but the long-term proportions are stable. The quantum experiment is more subtle because the probabilities themselves depend on interference between amplitudes rather than on a fixed list of independent classical roots. A particularly strange feature appears in the dark fringes. An electron sent through either path separately could reach some of these regions. When both coherent paths are available, the probability can fall almost to zero because the amplitudes cancel. Opening an additional route can therefore make an arrival less likely. That is not what independent classical particles should do. If each electron simply selected one slit while ignoring the other, the final distribution would be the sum of two single-path patterns. It would not contain deep interference minima created by cancellation. The experiment therefore presents its central paradox in a remarkably clean form. Every detection is particle-like, localized, and indivisible. Yet the long-term distribution behaves as though each electron was influenced by the complete two-path arrangement. The electron arrives at one place, but but the probability of that place depends on alternatives extending across the apparatus. Nothing about the result is uncontrolled or vague. Quantum mechanics predicts the fringe spacing, the relative intensity, and the shape of the distribution with extraordinary accuracy. What it does not provide is one simple classical account of what each electron was doing before it arrived. The interference pattern may look delicate and almost accidental as it develops one point at a time. Beneath it, however, lies a precise mathematical rule. The difficulty begins with the way ordinary probabilities normally behave. Suppose a classical particle can reach a screen by travelling through either the left slit or the right slit. If the two possibilities are independent, the probability of finding the particle at a particular location should be obtained by adding the probability for the left path to the probability for the right path. That is how familiar uncertainty works. Perhaps the particle definitely travelled through one slit, but we simply do not know which one. In that case, each route contributes its own ordinary distribution, and the final result is the sum of the two. Quantum mechanics does something different. It does not begin by assigning an ordinary probability to each path. Instead, it assigns a probability amplitude. A probability amplitude is not itself a probability. It is a mathematical quantity from which a probability can later be calculated. Unlike ordinary probabilities, amplitudes carry phase. In suitable descriptions, they can also have positive or negative values, or more generally complex values containing information that cannot be represented by an ordinary number line alone. The important point is not the unfamiliar mathematics itself, but the order in which the calculation is performed. When two alternatives remain coherent, the amplitudes are combined first. Only after they have been added is the probability calculated. This distinction was clarified by the German physicist Max Born during the development of quantum mechanics in the 1920s. Born proposed that the wave function should not be interpreted simply as a physical material wave spread through space. Instead, its squared magnitude gives the probability density for obtaining a particular result. The defining rule can be stated in plain language as the probability of an outcome is given by the squared magnitude of its probability amplitude. This became known as the Born rule. For a two-slit experiment, one amplitude is associated with the path through the first slit and another with the path through the second. When both alternatives remain coherent and no reliable path information exists, these amplitudes are added together. The central relationship can therefore be stated as the total probability is obtained from the squared magnitude of the sum of the path amplitudes. The sequence matters enormously. If probabilities were calculated for the paths separately and then added, the result would be two overlapping single-slit distributions. There would be no interference fringes. When amplitudes are added first, their phases affect the result. In some parts of the screen, the two-path amplitudes point in compatible directions within the mathematical description. They reinforce one another, producing a larger total amplitude and therefore a greater probability of detection. These are the bright fringes. Elsewhere, the amplitudes oppose one another. Their contributions partially or almost completely cancel before the squared magnitude is calculated. The total amplitude becomes small, so the probability of detecting an electron there also becomes small. These are the dark fringes. This produces one of the strangest features of the experiment. Either slit opened alone may allow electrons to arrive in a particular region. When both slits are opened coherently, that same region can receive almost no electrons. The second available route has not simply added another opportunity. Its amplitude has cancelled the contribution from the first. Ordinary probabilities cannot behave this way. Probabilities are never negative, and adding an extra positive probability cannot reduce the total. Probability amplitudes have a richer structure, allowing alternatives to reinforce or cancel before they become measurable probabilities. A useful comparison comes from waves, although the comparison should not be pushed too far. two water waves can overlap so that their heights add, producing a larger disturbance. They can also arrive out of step, allowing a crest to meet a trough and reduce the visible motion. Quantum amplitudes combine in a mathematically similar way. But the quantity interfering is not necessarily a material substance moving up and down in space. It is the amplitude structure encoded in the quantum state. The phase difference between the paths changes across the screen because the distances travelled through the two slits are not identical for every possible arrival point. At one location, the path lengths may differ by an amount that allows reinforcement. A little farther away, the difference may produce cancellation. This variation creates the regular sequence of high and low probabilities. The calculation predicts not merely that some sort of striped pattern will appear, but where the fringes should fall and how intense they should be. The electron wavelength, slit separation, opening width, and distance to the screen all contribute to the final distribution. The statistical nature of the prediction does not make it imprecise. Quantum mechanics may not state where the next electron will land, but it can specify the probability distribution followed by a very large number of electrons with remarkable accuracy. The distinction between a coherent superposition and a classical mixture is therefore essential. In a classical mixture, each electron would secretly take one path or the other. The experimenter might not know which route had been selected, but the alternatives would remain ordinary and independent. The final pattern would be obtained by adding the two-path probabilities. In a coherent quantum superposition, the alternatives retain a definite phase relationship. Their amplitudes combine, and the interference terms alter the final probability distribution. This is not merely a difference in language. The two descriptions predict visibly different results. A classical mixture gives two broad, overlapping bands. A coherent superposition gives interference fringes. The mathematics tells us exactly how to calculate the difference. It also tells us how the pattern should change if coherence is reduced or path information becomes available. What the mathematics does not settle is the physical meaning of the alternatives before measurement. Does the wave function describe something objectively real, extending through both paths? Does it encode possible experiences or available information? Does a particle follow one hidden trajectory while another part of the theory passes through both slits? Do the alternatives correspond to separate branches of reality? Quantum theory provides precise rules for combining possibilities, yet physicists do not universally agree about what those possibilities are. The pattern is predictable, the calculation is dependable, the reality beneath it remains open to interpretation. It is often said that an electron passing through two slits interferes with itself. The phrase captures something important. When electrons are sent through the apparatus one at a time, the interference pattern still develops. There is no second electron present for the first to interfere with. Whatever produces the pattern must therefore belong to the quantum description of each individual electron. But the phrase can also create an unhelpful picture. It may suggest that the electron is a tiny solid object that reaches the barrier, splits neatly into two smaller pieces, sends one half through each slit, and later rejoins itself before arriving at the screen. That is not what the detector records. Each electron arrives as one complete event. Its full electric charge is transferred at one location. Its energy is delivered in one local interaction. The screen does not receive half an electron in one bright fringe and the remaining half somewhere else. What spreads through the apparatus is the electron's quantum state. When the electron is prepared and sent towards the barrier, its wave function evolves according to quantum mechanics. If both openings are available and no physical process distinguishes the routes, the state develops amplitudes associated with both slits. These amplitudes remain coherent, meaning that their relative phase is preserved. Beyond the barrier, they overlap and combine. At some positions they reinforce one another, at others they cancel. The result is the probability distribution eventually revealed by many localized detections. This is the careful meaning behind self-interference. The quantum state of one electron contains coherent alternatives, and the amplitudes associated with those alternatives influence the probability of the final outcome. That description is more precise than saying that a classical particle literally divides itself. It is also more cautious than declaring that a tiny object definitely travels through both openings in the ordinary sense. Quantum mechanics directly predicts the probabilities of measurement outcomes. It tells us what pattern will appear on the screen, and how that pattern changes when the apparatus is altered. It does not provide one universally accepted account of an unseen microscopic journey between the source and the detector. Different interpretations describe that interval differently. The principle of superposition, closely associated with Paul Dirac's formulation of quantum mechanics, expresses the central mathematical idea. If several quantum states are possible, then combinations of those states can also form valid states. In a two-path experiment, the electron may be described by a superposition containing an amplitude for the first root and an amplitude for the second. This is not simply a statement that one root is real, while the experimenter happens to be ignorant of which one. An ordinary state of ignorance behaves differently. Imagine placing a small classical object into one of two sealed boxes. The object is definitely in one box, even if nobody knows which. Opening the boxes later reveals a fact that already existed. Probabilities can represent the observer's lack of knowledge, but the alternatives do not interfere. If an electron had simply chosen one slit in this classical way, the final result would be a mixture of two independent distributions. The electrons passing through the first slit would create one broad pattern. Those passing through the second would create another. Adding the two would not produce alternating bright and dark fringes. The observed interference therefore cannot be explained merely by saying that each electron takes one ordinary route, and we do not know which route it selected. A coherent superposition is physically different from classical uncertainty. The alternatives retain phase relationships, and those phases influence later probabilities. Richard Feynman expressed the same quantum structure through his sum over histories approach, also known as the path integral formulation. In this framework, the amplitude for a particle to travel from its preparation point to a final detection point is calculated by considering possible histories connecting the two. Each history contributes an amplitude carrying a phase. These contributions are then added. Some sets of histories reinforce one another, others largely cancel. The surviving combination determines the probability of the final detection. For the double slit, histories passing through both openings contribute to the total amplitude, when both routes remain available and coherent. Closing one slit removes an entire family of contributions, changing the final distribution. The phrase possible histories should not be interpreted too literally. Feynman's calculation does not require us to imagine countless miniature copies of one electron physically rushing along every conceivable classical route. The paths are elements within a mathematical procedure for calculating amplitudes. Whether they correspond to equally real histories, unrealized possibilities, parts of a wave function, or something else depends on the interpretation being used. The path integral can even include routes that appear wildly unlike the smooth trajectory expected from classical mechanics. The reason classical paths emerge for large objects is that neighbouring contributions reinforce strongly around the route of stationary action, while more erratic alternatives tend to cancel. At quantum scales, however, alternatives that classical intuition would dismiss can remain relevant to the final amplitude. This helps explain why the language of a single path becomes unreliable in the double-slit experiment. The quantum prediction is built from mutually available alternatives before a probability is assigned. Once a path detector creates a reliable distinction between the routes, the situation changes. The alternatives become correlated with different states of another physical system. They can no longer combine in the same simple, coherent way when the detector is ignored and the visible interference disappears. Nothing in this requires the electron to be consciously observed, nor does it require the electron to make a decision. The change follows from the structure of the combined quantum state. Self-interference is therefore both a useful phrase and an incomplete one. It correctly reminds us that a single electron does not need another electron to create interference. It also warns us that the relevant quantum state cannot be reduced to an ordinary unknown classical path, but it should not tempt us into imagining a little ball cutting itself in half and meeting itself again. The safest conclusion is narrower and stranger. A single quantum state contains coherent path alternatives. Their probability amplitudes combine, reinforce, and cancel. The resulting electron is always detected in one place, yet the distribution of those places depends on the full arrangement of possible routes. The mathematics is clear about how this happens. What those alternatives are in reality remains a matter of interpretation. Once the interference pattern appears, the most natural response is to look more closely. If an electron seems to be affected by both openings, perhaps the confusion can be resolved by placing a detector near the slits. The detector could reveal whether the electron passes through the left opening or the right one. Then the unseen journey would become clear. This sounds straightforward, but a path detector cannot discover the route without becoming part of the physical experiment. To record which slit was used, something in the detector must respond differently to the two possible paths. A photon might scatter from the electron near one opening. An atom beside a slit might change its internal state. A small cavity could gain an excitation. A marker could alter polarization. The barrier might receive a tiny recoil. Some physical system must carry a record that is correlated with the route. The exact design can vary, but the defining principle remains the same. The detector must end in one distinguishable state if the electron takes one path, and another distinguishable state if it takes the other. When the path information becomes reliable, the interference pattern disappears. The electrons still arrive individually. Each one still produces a localized point on the screen. The detector does not prevent them from passing through the apparatus, and it does not necessarily scatter them so violently that they miss the screen entirely. What changes is the distribution of the impacts. Instead of alternating interference fringes, the accumulated detections form a smoother pattern resembling two overlapping single-slit distributions. One contribution is associated with electrons passing through the first opening, and another with electrons passing through the second. The narrow regions of reinforcement and cancellation are gone. This is exactly what would have been expected from an ordinary classical mixture. If each electron travels through one slit or the other, and the alternatives no longer interfere, the total pattern is obtained by adding the two separate distributions. The remarkable part is that the change can be reversed. If the path marking detector is removed, switched off, or adjusted so that it no longer leaves distinguishable records, the interference pattern can return. This requires the source and the rest of the apparatus to preserve sufficient coherence. Uncontrolled interactions with the environment can still wash the pattern away, but under suitable conditions the sequence is clear. With both paths open and indistinguishable, interference appears. When the paths are marked and distinguishable, interference disappears. When the distinguishing interaction is removed, interference returns. This behavior is often described by saying that observation changes the result. That statement is not entirely wrong, but the word observation can be misleading. It may suggest that a conscious person must stare at the apparatus. It may sound as though an electron behaves like a wave until someone looks, then becomes embarrassed and quickly chooses a slit. Nothing in the experiment requires that sort of psychological drama. The detector can operate in an empty laboratory. Its output can be stored without anyone reading it. The data can even be discarded. If the route remains physically encoded in distinguishable states, the interference can still disappear. The relevant change is not that a human mind has gained knowledge. The change is that the total physical system now contains a reliable correlation between the electron's path and something else. Suppose a detector beside the left slit changes from its initial state to one marked state when the electron passes nearby. A second detector beside the right slit changes to a different state if the other path is used. After the interaction, the electron and detectors are no longer described independently. The left path contribution is linked with one detector record, while the right path contribution is linked with another. If those records are distinguishable, the path alternatives no longer behave like two unmarked amplitudes belonging to one isolated electron state. The surrounding apparatus has become involved. This remains true even when the record is subtle. A scattered photon may travel away carrying path information. No scientist needs to catch it. An atom may be left in a different energy state. No display needs to show the result. A vibration, recoil, or environmental interaction may encode enough information to distinguish the roots in principle. The phrase "in principle" must also be handled carefully. It does not mean that a person could necessarily recover the information with convenient equipment. It means that the physical states associated with the alternatives have become sufficiently distinct that they no longer overlap in the way required for visible interference. If the two detector states are only partly distinguishable, the fringes do not always vanish completely. Their contrast may simply become weaker. This reveals that the change is not always an abrupt switch between perfect waves and perfect particles. There is a continuous trade-off. As reliable path distinguishability increases, interference visibility generally decreases. A poorly resolved detector may provide only a hint of the route, leaving faint fringes. A highly effective detector can make the path nearly certain and suppress the pattern almost entirely. The experiment therefore does not show that the electron reacts to curiosity. It shows that coherent alternatives are sensitive to physical correlations. This raises a further question. Perhaps the detector destroys interference simply because it disturbs the electron. Any measurement requires an interaction. A scattered photon can transfer momentum. A barrier can recoil. An electric or magnetic field can alter the electron's motion. It might seem that the path detector gives the electron a small random kick, blurring the fringes until they disappear. In many practical experiments, such disturbance is certainly present. Measurements can push, heat, scatter, and redirect quantum systems. A sufficiently large uncontrolled kick would indeed damage an interference pattern. But mechanical disturbance is not the complete explanation. It is possible to design path-marking arrangements in which the momentum transferred to the particle is too small or too carefully controlled to explain the loss of interference as an ordinary blur. The pattern can still vanish because the route has become correlated with distinguishable detector states. The deeper issue is therefore not simply whether the electron was bumped, it is whether the two path alternatives remain capable of combining as one coherent quantum state. Watching the slits changes the experiment because a genuine path record must be created physically. That record joins the electron to the detector and, often, to the wider environment. The electron does not need to know that it has been watched. The universe only needs to contain a mark of where it went. The language of observation can make the double-slit experiment sound more mysterious than it needs to be. An observer may suggest a person watching a screen or reading a result. In the physics itself, the important processes are interaction, correlation, entanglement, and path distinguishability. Before any path detector is introduced, the electron is described by one coherent quantum state. That state contains an amplitude associated with the first slit and another associated with the second. Because the two alternatives remain coherent, their relative phase is preserved. When the amplitudes later overlap at the detection screen, they can reinforce or cancel. The screen then reveals alternating regions of high and low probability. Nothing outside the electron has yet recorded which path was taken. A path detector changes that situation by responding differently to the two routes. Imagine a detector beginning in one neutral state. If the electron passes through the left slit, the detector evolves into a particular marked state. If the electron passes through the right slit, it evolves into a different marked state. The electron's path has now become correlated with the detector. The left path amplitude is linked with one detector state. The right path amplitude is linked with another. the electron and detector can no longer be described completely as separate systems with independent states. They have become entangled. Entanglement means that the full quantum state belongs jointly to both systems. It contains correlations that cannot be represented by assigning one complete state to the electron and another complete state to the detector. The electron is therefore no longer in the same isolated coherent state it possessed before the interaction. This is sometimes described by saying that the electron has become mixed when considered on its own. More precisely, the combined electron detector system may remain in a pure quantum state, while the electron's reduced state no longer contains the same accessible coherence between the paths. The distinction matters. Quantum evolution has not necessarily stopped. Nothing in the fundamental equations requires the total system to abandon quantum mechanics. Instead, the coherence has been transferred into correlations between the electron and detector. To understand why the visible fringes disappear, imagine that the two possible detector states are clearly distinguishable. One detector state belongs to the left path, the other belongs to the right path. When the electron reaches the screen, its position is therefore still linked with information stored elsewhere. If the detector is ignored and only the unsorted electron impacts are examined, the interference contributions no longer combine in the same way. In the original unmarked experiment, the probability distribution contains cross terms. These cross terms arise from combining the amplitude for the first root with the amplitude for the second. They are the mathematical contributions responsible for reinforcement and cancellation. Once the roots are correlated with distinguishable detector states, those cross terms are suppressed in the electron's reduced description. The detector states associated with the paths no longer overlap sufficiently for the alternatives to interfere in the ordinary unsorted screen pattern. The resulting electron distribution resembles the sum of two single-path distributions. It is important that this loss of visible interference does not require the combined state to have become classical. The full electron detector system can still be described by quantum mechanics. The coherence has not necessarily vanished from existence. It has become encoded in a more complicated joint state. Recovering it would require controlling the detector as well as the electron, and arranging the correlations in a way that allows the alternatives to be recombined. In carefully designed quantum eraser experiments, related forms of coherence can indeed be revealed in selected correlations. For an ordinary path measurement, however, the detector is usually ignored or allowed to interact with an even larger environment. The interference then becomes inaccessible. This understanding was sharpened by work from Marlon Scully, Berthold Georg Englert, and Herbert Walter. Their quantum optical analyses examine path detection using arrangements in which atoms or photons became correlated with internal detector states. They showed that interference could disappear even when there was no large uncontrolled mechanical kick capable of simply blurring the pattern. This challenged the easy explanation that all path measurements destroy fringes only by violently disturbing the particle's momentum. Mechanical disturbance can matter, but distinguishability is the deeper and more general principle. The detector does not need to push the electron sideways by a large amount. It only needs to become sufficiently different depending on which route is taken. Nor does the detector need to present a human-readable result. There does not have to be a flashing sign announcing left slit or right slit. No computer screen needs to display a label. Nobody has to save the information in a convenient file and remember the password. The two detector states simply need to be distinguishable in principle. One state might contain an excited atom while the other does not. One cavity might hold a photon while another remains empty. A polarization marker might rotate in one direction for one route and another direction for the other. A microscopic recoil could become correlated with the path. These physical distinctions are enough. If the two detector states are perfectly distinguishable, the ordinary interference visibility can fall to zero. If they overlap partially, some coherence remains and the fringes become weaker rather than disappearing completely. This gives the process a continuous character. The electron is not forced to choose between being entirely wave-like and entirely particle-like through an abrupt act of observation. Instead, the amount of visible interference depends on how strongly the path becomes correlated with distinguishable external states. The stronger the path information, the weaker the unsorted interference pattern. This small interaction between one electron and one detector also reveals how the wider classical world emerges. A macroscopic object is never truly isolated. Air molecules collide with it. Thermal radiation is emitted and absorbed. Light scatters from its surface. Internal vibrations become correlated with position. Nearby materials respond to its electric, magnetic, and gravitational influence. Each interaction can carry away information about where the object is and what it is doing. The environment therefore behaves like an enormous, uncontrolled collection of path detectors. Countless degrees of freedom become entangled with the object. Phase relationships between macroscopically different alternatives spread into correlations that are effectively impossible to track or reverse. This process is called decoherence. The path detector in the laboratory provides a controlled, simplified example of the same mechanism. One quantum system leaves a record in another. The original alternatives become correlated with different external states. When those external states are ignored, interference fades from the observable distribution. The particle has not become classical because someone looked at it. It has become entangled with a world capable of remembering where it went. One of the oldest explanations for the disappearance of interference is also one of the most intuitive. To discover which slit a particle passes through, something must interact with it. That interaction may change the particle's motion. A photon used to illuminate an electron can scatter from it and transfer momentum. A detector near one opening can exert a force. The barrier itself may recoil slightly. Electrical noise, vibrations, or uncontrolled fields may alter the particle's path. From this perspective, the interference pattern disappears because the measurement has disturbed the electron. The idea has real physical content. Many practical detectors do disturb the systems they measure. If the particle receives a sufficiently random sideways kick, the carefully arranged phase relationship between the two paths can become blurred. The fringes then weaken or disappear when many altered trajectories are combined. A rough measurement can therefore destroy interference in a very ordinary way. This explanation is closely connected with early discussions of the uncertainty principle. To locate a particle precisely near one slit, a short wavelength probe may be required. A short wavelength corresponds to a relatively large momentum, so the probing photon can transfer enough momentum to make the electron's later position less predictable. In that kind of arrangement, greater path resolution comes with greater disturbance. But mechanical disturbance is not the whole story. Carefully designed experiments can mark the two paths without delivering a large, uncontrolled momentum kick capable of washing the pattern away through a simple classical blur. The particle can continue towards the screen with nearly the same overall momentum distribution, yet the visible interference still disappears. What changes is the distinguishability of the alternatives. A path marker must respond differently depending on which route is taken. Perhaps one atomic state becomes excited for the first path and another for the second. Perhaps two possible photon polarizations are attached to the alternatives. Perhaps one cavity stores an excitation while another remains empty. The important feature is that the physical states associated with the paths can be told apart. This is what quantum information means in the double-slit experiment. It is not an abstract fact floating somewhere outside the apparatus. It is not knowledge waiting patiently inside a notebook. It is a physical correlation between distinguishable states. If the first path leaves the detector in one state, and the second leaves it in another, then the detector contains path information. Whether anyone actually reads it is secondary. The effect depends on how distinguishable those states are. If the two detector states are completely indistinguishable, they provide no reliable clue about the route. The path amplitudes can remain highly coherent and a strong interference pattern can appear. If the detector states are only partly distinguishable, limited path information becomes available. The interference pattern remains, but the contrast between bright and dark fringes is reduced. If the states are fully distinguishable, the path can in principle be identified with certainty. In that case, full interference disappears from the unsorted detection pattern. The transition between these situations is continuous. Fringe visibility describes how strongly the bright and dark bands differ. High visibility means the bright fringes are pronounced, and the dark fringes are deep. Low visibility means the pattern is faint or almost completely washed out. Path distinguishability measures how well the two routes can be discriminated from the available physical record. Berthold Georg Englert expressed the trade-off between these quantities in a precise quantitative relation. Written in words, it states that visibility squared plus distinguishability squared cannot exceed 1. This relation captures complementarity in a measurable form. If path distinguishability is close to 1, meaning the route can be identified almost perfectly, the maximum possible fringe visibility must be close to 0. If fringe visibility is close to 1, meaning the interference is nearly perfect, path distinguishability must be close to 0. Intermediate cases lie between these limits. Some path knowledge can coexist with some interference, but neither can reach its maximum while the other remains substantial. The relation does not say that every imperfect experiment exactly reaches the limit. Additional noise, technical flaws, or environmental interactions may reduce the visibility further. It states the maximum combination permitted by the quantum state. This reveals why the language of information must remain grounded in physics. Suppose a detector stores the route in two distinct atomic states. Even if the states are never converted into words, numbers, or pictures, they are physically distinguishable. A suitable later measurement could tell them apart. The path information therefore exists as a correlation. By contrast, if the two detector states are identical, no later procedure can extract the route from them. There is no physical path record, and the alternatives may continue to interfere. Information in this setting means the possibility of distinguishing physical states, not the presence of a conscious observer who understands the result. The same point can be seen by imagining that the detector's memory is immediately sealed inside a box. Nobody opens it. Nobody knows which slit was recorded. The interference does not return merely because the laboratory staff remain uninformed. Human ignorance is not the same as quantum indistinguishability. If the two path records remain different inside the box, the electron is still entangled with them. The unsorted position distribution still lacks full interference. This is why the disappearance of the fringes cannot be reduced to a mystical reaction to attention. The electron does not respond to curiosity, awareness, or intention. It responds, in the language of quantum theory, to the physical structure of the total state. Mechanical disturbance often accompanies measurement, and in some experiments it provides a useful practical explanation for reduced interference. But the more general principle is path distinguishability. The pattern fades when the alternatives become correlated with external states that can reveal which route occurred. The experiment therefore exposes a trade-off between two kinds of experimental evidence. One arrangement preserves coherence and reveals interference. Another records the path and reveals which-way information. As one becomes clearer, the other becomes less available. There is no need to imagine matter sensing that it has been watched. The universe is doing something quieter and more precise. It is keeping track of correlations. The double-slit experiment seems to offer two different kinds of evidence. With both paths open and no reliable record of the route, an interference pattern develops. The final distribution contains alternating regions of high and low probability, revealing the influence of coherent amplitudes associated with both openings. When the apparatus is changed so that the path can be identified, the interference disappears. Each electron can then be associated with one route or the other, and the screen shows the smoother distribution expected from two distinguishable alternatives. Niels Bohr developed the principle of complementarity to describe this relationship. Complementarity says that certain aspects of a quantum system can be revealed only through different, mutually incompatible experimental arrangements. Wave-like interference and particle-like path information are not simply two incomplete views waiting to be combined by a better piece of equipment. The conditions needed to reveal one prevent the full appearance of the other. In an arrangement that preserves coherence, the two path amplitudes retain a stable phase relationship. They can reinforce and cancel, producing interference fringes. In an arrangement that records the route, the alternatives become correlated with distinguishable detector states. Reliable path information becomes available, but the interference is suppressed. The experimenter cannot construct one arrangement that provides perfect interference and perfect path knowledge at the same time. This is not merely an engineering inconvenience, it reflects the structure of quantum theory. Bohr did not mean that the electron secretly possesses a complete set of ordinary wave and particle properties, while scientists happen to lack sufficiently delicate instruments to reveal them all. His claim was more radical. The experimental arrangement helps define which physical concepts can be meaningfully applied. A wave description becomes useful when the apparatus preserves coherent alternatives and reveals phase-dependent interference. A particle path description becomes useful when the apparatus provides distinguishable routes and localized records. These descriptions are complementary because both are required for a complete account of quantum phenomena. Yet the experimental conditions needed to display them fully cannot be realized together. Werner Heisenberg's uncertainty principle is closely related to this idea, although the two concepts are not identical. The uncertainty principle places mathematical limits on how sharply certain pairs of observables can be defined within one quantum state. The best-known example involves position and momentum. The relationship can be expressed in words as the uncertainty in position multiplied by the uncertainty in momentum cannot be smaller than a limit determined by Planck's constant. This is sometimes explained as a problem caused by clumsy measurement. A scientist tries to locate a particle, accidentally knocks it, and therefore loses track of its momentum. Such disturbance can certainly occur, but the uncertainty principle reaches deeper. Even an ideally prepared quantum state cannot possess arbitrarily precise values of position and momentum at the same time. A state tightly confined in position requires a broad range of momentum amplitudes. A state with sharply defined momentum must be spread widely across space. This follows from the mathematical relationship between the two descriptions, not merely from imperfect instruments. Uncertainty, therefore, concerns limits on the simultaneous sharpness of certain observables. Complementarity concerns the experimental conditions required to reveal different aspects of a quantum phenomenon. The ideas overlap because many complementary arrangements involve incompatible observables. A precise attempt to determine which slit an electron uses often involves localizing it near one opening, which may affect the available momentum information and disturb the phase relationships needed for interference. Yet complementarity is broader than this particular disturbance. The disappearance of interference can also arise through entanglement with a path marker, even when no large random momentum kick is delivered. The essential change is that the paths become distinguishable. The double-slit experiment provides an especially clear example. When both openings remain coherent, the apparatus reveals interference. The accumulated pattern depends on relative phase and resembles the behavior associated with waves. When path detection is introduced, the apparatus reveals which way information. The electron is found through one route or the other, and the interference pattern disappears. It is tempting to call the first arrangement a wave experiment and the second a particle experiment. That language is useful, but it requires care. Even in the interference arrangement, every completed detection is localized. Each electron arrives as one distinct point on the screen. The pattern is wave-like, but the individual event is particle-like. The experiment therefore never displays a classical wave in the ordinary sense. A water wave spreads its energy across a region and can be detected at many places at once. An electron deposits its charge and energy in one local event, Similarly, the path marking arrangement does not reveal a perfectly classical particle unaffected by quantum rules. The electron remains a quantum system. Its possible outcomes, detector correlations, and statistical distribution are still calculated through quantum mechanics. The language of waves and particles is therefore borrowed from classical physics. Each concept captures part of the observed behaviour, but neither provides a complete standalone picture. Bohr placed great importance on this limitation. He resisted attempts to describe a microscopic object as though it possessed a complete independent set of classical properties, detached from the apparatus used to study it. In his view, a quantum phenomenon included not only the system, but also the experimental conditions under which a result became definite and communicable. This did not mean that laboratory equipment created the external universe from nothing, nor did it mean that nothing existed before measurement. It meant that statements such as the electron followed a particular path, or the electron behaved as a wave, gained their precise physical meaning from the arrangement used to establish them. A path is not merely a hidden line waiting to be uncovered without consequence. It becomes an experimentally defined property through a physical interaction capable of distinguishing one route from another. Interference is not simply a visual decoration added to an otherwise classical journey. It appears when the alternatives remain coherent and cannot be assigned independent identities. The formal predictions are clear. Quantum mechanics tells scientists when fringes will appear, when they will fade, and how path distinguishability limits their visibility. The interpretive meaning remains disputed. Some physicists regard complementarity as a fundamental lesson about what can meaningfully be said of quantum reality. Others see it mainly as a disciplined rule for discussing measurements, while leaving deeper questions unanswered. Pilot wave theories assign definite particle trajectories while retaining a guiding wave. Many worlds' interpretations preserve the full quantum state without fundamental collapse. Objective collapse theories modify the dynamic so that one result is physically selected. These approaches disagree about the reality beneath the experiment, yet they reproduce the same familiar trade-off between path information and interference within their tested domains. Complementarity, therefore, does not end the mystery. It describes the boundary encountered whenever classical concepts are pushed into the quantum world. The electron is detected as one local event. Its distribution reveals coherent alternatives. The apparatus can expose the path or preserve the interference, but it cannot make both classical pictures complete at once. Reality has not chosen to be either a wave or a particle. It has simply refused to fit entirely inside either idea. The quantum eraser takes the logic of the double-slit experiment and turns it into something even more subtle. In an ordinary two-path experiment, interference appears when the alternatives remain coherent and indistinguishable. If the paths are marked so that one can be told from the other, the visible fringes disappear. The quantum eraser asks whether that distinction can be removed. The word eraser can be misleading. Nothing is dragged backwards through the apparatus. No photon retraces its journey. No electron is repaired after being disturbed. A known historical fact is not deleted from someone's memory. What is erased is the distinguishability of the path markers within the relevant measurement arrangement. Consider a photon approaching two possible paths. The first route might become associated with horizontal polarization, while the second becomes associated with vertical polarization. These two polarization states are orthogonal, meaning they can be distinguished perfectly by a suitable measurement. The photon's route is now correlated with a physical marker. If it travels through the first path, it carries one polarization. If it travels through the second, it carries the other. The alternatives no longer remain unmarked contributions belonging to one simple coherent state. When only the photon's final position is recorded and the polarization is ignored, the ordinary interference pattern disappears. The same principle can be implemented in other ways. One path may leave an atom in one internal state, while the other leaves it in another. Different cavities may acquire distinct excitations. In experiments using entangled photon pairs, The route of one photon may become correlated with the state or later detection of its partner. In every case, path information becomes physically available because the alternatives are connected to distinguishable states. The quantum eraser changes the way those marker states are measured. Suppose horizontal polarization identifies one route and vertical polarization identifies the other. Instead of measuring in the horizontal and vertical basis, the apparatus can measure in a rotated basis. A rotated polarization state may contain an equal combination of the original horizontal and vertical components. Another rotated state can contain the same components with a different relative phase. When the detections are sorted according to these rotated marker outcomes, the original path distinction is no longer present within each selected subgroup. The first subgroup contains contributions from both paths combined in one phase relationship. The second also contains contributions from both paths, but with the opposite phase relationship. Each subgroup can display interference. One may produce an ordinary fringe pattern. The other produces an anti-fringe pattern, with its bright regions falling where the first pattern has dark regions. This is an essential detail. The complete unsorted collection of detections still shows no visible interference. The fringe and anti-fringe patterns overlap and cancel when they are added together. Only after the events are grouped according to the corresponding marker results does the hidden interference structure become visible. The quantum eraser therefore does not restore one universal pattern to the original screen. It reveals complementary interference patterns inside correlations between different parts of the experiment. This prevents the arrangement from becoming a method for sending secret messages through quantum strangeness. An observer looking only at the first detector sees a random distribution with no readable fringes. The local results do not reveal how the distant marker will later be measured. To identify the correlated subgroups, records from both sides must be brought together through ordinary communication. That comparison cannot travel faster than light. The central idea was proposed by Marlon Scully and Kai Druhl in the early 1980s. Their analysis showed that which path information could be erased by changing how the correlated marker was measured, allowing interference to reappear within selected results. The proposal sharpened an important distinction. The loss of interference did not always require a large mechanical disturbance to the particle's motion. The decisive change could arise because the paths had become correlated with distinguishable quantum states. Later experiments brought the idea into the laboratory in increasingly striking forms. One widely discussed implementation was carried out by Yoon-Ho Kim and collaborators. Their experiment used entangled photons created together in a nonlinear optical process. One photon, often called the signal photon, travelled towards a detector capable of recording its position. The other, called the idler photon, entered an arrangement containing several possible detectors. Some idler detections preserved information that could identify the signal photon's corresponding path. Other detections erased that distinction by combining the alternatives in a different basis. When the signal detections were sorted according to which idler detector had fired, different patterns emerged. The subsets associated with preserved path information showed no interference. The subsets associated with erased path distinguishability produced complementary fringe and anti-fringe patterns. Again, the complete unsorted signal data showed no visible interference. This point is often lost in dramatic descriptions of the experiment. The later choice of measurement does not alter an already visible image on the earlier screen. The earlier detector does not display a clear pattern that suddenly changes when someone adjusts equipment elsewhere. Every local signal detection remains one fixed event. What changes is how those events can later be grouped according to their correlations with the idler results. The quantum eraser therefore does not rewrite the past. It does not prove that a later decision reaches backwards in time and instructs a photon how it should previously have behaved. Such language assumes that the photon must have possessed one simple classical history throughout the experiment. Quantum mechanics instead describes a joint entangled state. The correlations predicted by that state do not require one measurement to send a causal influence into the past. The order in which the records are examined does not change the statistical relationships between them. An experimenter may read the signal results first, the idler results first, or both much later. The same joint correlations are found when the data are compared. Nor does the quantum eraser depend upon a person choosing to know or forget the path. If the marker is measured in a path-revealing basis, the corresponding correlations preserve which-way information. If it is measured in an erasing basis, the resulting subgroups combine path amplitudes differently. The physics depends on the measurement basis and the structure of the entangled state, not on anyone's emotional commitment to opening the laboratory notebook. This makes the experiment strange in a very specific way. The same set of localized quantum events can be organized into different correlated patterns depending on which compatible marker property is measured. One arrangement reveals path distinction, another reveals interference within selected subsets. Neither provides perfect path information and full interference in the same subgroup. Complementarity remains intact. The quantum eraser does not remove the rules of quantum mechanics. It displays them with unusual clarity. Path information is not merely a story told after the particle arrives. It is encoded in physical correlations. Interference depends on whether the alternatives remain distinguishable within the particular set of results being examined. Nothing travels backwards to repair the journey. Nothing communicates faster than light. Nothing changes an event that has already been recorded. What changes is the way coherent alternatives are preserved, marked, and recombined within an entangled quantum system. The path is not erased from history. Its distinguishability is erased from a correlation. John Archibald Wheeler asked a deceptively simple question. What happens if the experimenter delays the choice of what kind of measurement to perform until after the photon has already entered the apparatus? The ordinary double-slit experiment seems to offer two incompatible arrangements. Preserve both coherent paths and interference appears. Mark the route, and path information becomes available while the interference disappears. It is tempting to imagine that the photon somehow prepares for whichever experiment lies ahead. Perhaps it leaves the source as a wave when an interference measurement is waiting. Perhaps it leaves as a particle when the apparatus will reveal a definite path. In that story, the photon quietly chooses its identity at the beginning and carries it through the experiment. Wheeler's delayed choice thought experiment was designed to make that explanation difficult to maintain. A Mach-Zehnder interferometer provides a particularly clear way to understand the idea. It is a two-path optical arrangement that performs the same essential role as a pair of slits, while giving the experimenter greater control over how the paths are separated and recombined. A single photon first reaches a beam splitter. A beam splitter is a partially reflective optical device. It can transmit light along one route and reflect it along another. In a classical description of an intense beam, part of the light travels through each path. For a single photon, the quantum state develops a coherent amplitude associated with the transmitted route, and another associated with the reflected route. Mirrors guide these two paths through separate parts of the apparatus. They may travel several meters apart or follow routes designed to preserve a stable relative phase before reaching the final measurement region. At that point, the experimenter has two broad choices. A second beam splitter can be placed where the paths meet. This recombines the path amplitudes. Depending on their relative phase, they reinforce at one output and cancel at the other. With the interferometer adjusted carefully, nearly every photon may arrive at one detector while the other receives almost none. That is interference. The result cannot be explained simply by saying that half the photons travelled along the first route and half along the second. If that were all that happened, both output detectors would receive substantial numbers of photons. The strong preference for one detector depends on the coherent combination of amplitudes from both paths. The other choice is to remove the final beam splitter. Without that device, the paths do not recombine. Each route leads directly to a different detector. A detection at one output can then be associated with one path, while a detection at the other corresponds to the second. This arrangement provides path information. Wheeler asked what happens if the decision to insert or remove the final beam splitter is made only after the photon has passed the first beam splitter and entered the interferometer. By then, according to a naive classical story, the photon should already have made its choice. If it travelled through one definite path as a particle, the later insertion of the beam splitter should not somehow transform its earlier journey into a wave-like one. If it spread through both paths as a wave, the later removal of the beam splitter should not retrospectively force it to have used only one route. Yet quantum mechanics predicts that the final statistics depend on the measurement arrangement actually completed. When the paths are recombined coherently, interference appears. When the final beam splitter is absent and the routes lead to separate detectors, path information becomes available. The timing of the choice does not force the system to reveal a hidden decision made at the source. Experimental versions of Wheeler's idea have used fast optical switches, random choices, and single photons to ensure that the measurement arrangement is selected only after the photon has entered the apparatus. Vincent Jacques, Alain Aspect, Jean-François Roch, Philippe Grangier, and their collaborators carried out an especially clear realization using a single photon source and a rapidly controlled interferometer. Their apparatus made the decision between the open and closed configurations while the photon was already travelling inside. In the closed configuration, the final beam splitter recombined the paths and produced interference. In the open configuration, the paths remained separate and the outputs revealed which route was associated with the detection. The choice was made rapidly enough that no ordinary signal travelling at or below the speed of light could inform the photon, while it was still near the entrance, which configuration would eventually be used. The results followed the predictions of quantum mechanics. This can sound as though the future measurement reaches backwards and changes what the photon previously did. That is not required. The suggestion of retroactive change arises only if the photon is assumed to possess a complete classical biography throughout the experiment. In that biography, it must already have been either a particle following one route or a wave travelling through both. A later choice then seems forced to rewrite the earlier story. Quantum mechanics does not assign that simple history in the first place. Before the final measurement arrangement is completed, the photon is described by a quantum state containing coherent path amplitudes. The theory predicts how that state interacts with whichever measurement is eventually implemented. If the paths are recombined, their relative phase influences the detector probabilities. If they are measured separately, the output becomes correlated with path identity. The experiment therefore changes what can be meaningfully inferred about the route. It does not necessarily change an independently existing classical journey. The statistics depend on the complete physical arrangement, including the way the alternatives are eventually brought together or kept apart. This is not the same as saying that an observer's later thought controls the past. The choice must be implemented through real optical equipment. Beam splitters, switches, detectors, and path correlations determine which measurement is performed. The photon does not respond to a private decision made in someone's mind. It responds to the apparatus with which it interacts. Wheeler's delayed choice experiment should also be distinguished from the delayed choice quantum eraser. Both challenge the idea that each quantum system carries one simple classical history through the apparatus, but the arrangements are different. In Wheeler's basic delayed choice experiment, the late decision determines whether two paths are recombined to reveal interference or kept separate to reveal route information. A delayed choice quantum eraser usually involves entanglement with a second system. Path markers are preserved or erased within correlations, and interference appears only after detections are sorted into particular subgroups. In the quantum eraser, the complete unsorted local pattern remains without visible fringes. The interference appears in conditional correlations between linked measurements. In Wheeler's simpler interferometer, the open or closed configuration directly determines the output statistics for the photon travelling through that apparatus. Neither experiment permits usable messages to be sent into the past. Neither allows a later choice to alter a local detection that has already been irreversibly recorded. Neither lets one observer control an earlier outcome by selecting a convenient future measurement. They instead expose the failure of a particular classical assumption, that the photon must have privately decided at the source whether it would behave as a wave or a particle. The experiment does not support that fixed identity. A photon does not leave the source carrying a small label marked wave, waiting to interfere if the equipment is suitable. Nor does it carry a label marked particle, guaranteeing one ordinary route regardless of how the paths are later treated. Wave-like interference and path-like information emerge from different experimental relationships. The complete arrangement determines which set of correlations becomes observable. This leaves quantum theory with an unusual but consistent lesson. The past cannot always be described as a sequence of definite classical properties waiting to be uncovered later. What can be said depends partly on the physical measurement that is eventually completed. The photon does not need to receive instructions from the future. It only needs to remain quantum long enough for the final arrangement to matter. A path detector does not need to be a carefully designed laboratory instrument. In the wider world, almost everything is being measured constantly by its surroundings. Air molecules collide with objects and scatter away, carrying traces of their positions. Light reflects from surfaces and travels outward. Warm bodies emit thermal radiation. Nearby materials respond to electric and magnetic fields. Internal vibrations become correlated with motion, shape, and location. Each interaction can act as a tiny path marker. This is the central idea behind decoherence. In a carefully isolated double-slit experiment, the amplitudes associated with different paths preserve a stable phase relationship. Because that phase remains available, the alternatives can later overlap, reinforce, and cancel. Once the particle interacts with its environment, however, information about the paths begins to spread into surrounding degrees of freedom. A degree of freedom is simply an independent physical feature that can vary. It might be the direction of an escaping photon, the momentum of an air molecule, the vibration of a chemical bond, the state of a detector atom, or the motion of some part of the apparatus. When these features become correlated with the path, the quantum state no longer belongs to the particle alone. It belongs jointly to the particle and its environment. The different path alternatives become entangled with different environmental states. This process was explored in early foundational work by the German physicist Heinz-Dieter Zeh, commonly known as Heinz-Dieter Zeh. During the second half of the 20th century, Zeh argued that the apparent transition from quantum behavior to classical behavior could be understood through the unavoidable entanglement of systems with their surroundings. Wojciech Zurek later developed these ideas into the modern theory of environment-induced decoherence. Zurek examined how the environment continually monitors certain properties of physical systems. In many ordinary situations, position is especially stable because light, air molecules, and nearby matter repeatedly become correlated with where an object is located. Some quantum states survive this environmental monitoring more reliably than others. Zurek called these robust states pointer states. The name comes from the pointer on a measuring device. A useful pointer needs to remain in one stable position long enough to be read. A pointer that instantly spread into a visible superposition of every possible reading would be scientifically impressive, but administratively inconvenient. Pointer states are selected by the form of the interaction between a system and its environment. They are the states least rapidly disrupted by environmental monitoring. The wider process through which particular stable states become favoured is known as environment-induced superselection, sometimes shortened to Ein's election. This does not mean that the environment consciously chooses a result. It means that interactions preserve some states, while rapidly suppressing observable coherence between others. The effect is extraordinarily powerful for large objects. A microscopic particle may be isolated well enough for coherent alternatives to survive for a useful length of time. A macroscopic object contains enormous numbers of particles and presents a much larger surface to its environment. Imagine a grain of dust in a room. Air molecules strike it continually. Thermal photons are emitted from it. Background light scatters from its surface. Each interaction carries away a small amount of information about the grain's position. If the grain were placed into a superposition of two noticeably separated locations, the surrounding environment would rapidly become correlated with those alternatives. Photons scattered from the first position would travel in slightly different directions from photons scattered from the second. Air molecules would rebound differently. The internal vibrations of the grain could also evolve in distinguishable ways. After enough interactions, the two environmental states would become effectively orthogonal, meaning that they could be distinguished almost perfectly. At that point, the phase relationship between the grain's two positions would still exist somewhere in the enormous combined quantum state, but it would no longer be accessible through observations of the grain alone. The coherence would be dispersed across a vast network of correlations. This can happen extremely quickly. The exact decoherence time depends on the size of the object, the distance between the alternatives, the temperature, the pressure, the surrounding radiation, and many other details. For a large object in an ordinary room, decoherence between macroscopically distinct positions can occur on timescales far shorter than anything directly perceptible. The surrounding world records the object's location so efficiently that visible interference has no practical opportunity to develop. Vacuum chambers, low temperatures, vibration isolation, and electromagnetic shielding are therefore essential in matter wave experiments. Even one collision with a stray gas molecule can reveal enough path information to reduce interference. A single thermal photon emitted from a large molecule may carry away information about its route. Internal molecular motions can become entangled with the center of mass position and weaken coherence. The environment does not need to create a readable label. No air molecule carries a tiny note saying that the particle used the left slit. It only needs to end in a state that differs according to the path. Once many such states become involved, reversing the process becomes overwhelmingly difficult. In principle, quantum evolution can remain reversible. If every scattered photon, every air molecule, every vibration, and every detector state could be controlled with perfect precision, the loss phase relationships might be recombined. In practice, the number of environmental degrees of freedom grows almost immediately beyond any realistic possibility of control. Decoherence, therefore, does not usually mean that the universal wave function has been physically destroyed. According to the standard equations, the combined state of system and environment can continue evolving smoothly. What disappears is the locally observable interference between alternatives when the environment is ignored. Mathematically, scientists describe the object using a reduced state obtained by leaving out the inaccessible environmental details. That reduced state resembles a classical statistical mixture. It looks as though the object simply occupies one possible position or another with ordinary probabilities, rather than existing in a coherent superposition. The resemblance explains a great deal about the classical world. It helps account for why chairs remain in stable locations, why measuring devices display definite-looking readings, and why planets follow approximately continuous trajectories rather than spreading into visible interference patterns. These classical behaviors are not produced because large objects escape quantum mechanics. They arise because large objects become entangled with their environment so quickly and thoroughly that quantum coherence between distinct alternatives becomes effectively hidden. The double-slit experiment is therefore not separate from everyday reality. It reveals what ordinary reality would look like if environmental path marking could be suppressed. Electrons, atoms, and molecules can interfere when they are isolated well enough. Larger systems become harder to protect, because more of their surroundings can learn which path they take. An ordinary object moving through two openings is continually illuminated, heated, struck by molecules, and internally vibrating. Long before it reaches a screen, its possible paths have been recorded across an enormous environment. The interference has not necessarily been forbidden by size alone. It has been hidden by information spreading outward. Decoherence explains this disappearance of observable interference with remarkable success. It connects controlled path detection in the laboratory with the stability of the familiar macroscopic world. Yet one major question remains. Decoherence explains why different outcomes stop visibly interfering and why observers encounter stable, classical-looking alternatives. By itself, however, it does not universally explain why one particular outcome is experienced. The total quantum state may still contain separate decohered alternatives. The equations alone do not obviously select one and delete all the others. Decoherence tells us why the branches no longer overlap. It does not on its own tell every interpretation why only one branch appears to become reality. Decoherence explains why interference becomes hidden when a quantum system becomes entangled with the detector or environment. It explains why distinct alternatives stop visibly overlapping and why the world begins to resemble a collection of stable, classical outcomes. But it leaves behind a deeper question. Why does one definite result occur? At the level of the wave function, quantum mechanics usually describes change through the Schrödinger equation. This evolution is continuous, predictable, and deterministic. If the wave function is known at one moment, the equation determines how it develops at later moments. The evolution is also unitary, meaning that the total probability is preserved and the mathematical structure of the state changes smoothly. Nothing in this ordinary evolution instructs a superposition to select one of its components. If a quantum system begins in a state containing several possible outcomes, the Schrödinger equation generally carries all of those possibilities forward. It can alter their phases, spread them through space, or entangle them with other systems, but it does not normally choose one alternative and erase the rest. This becomes clear in the double-slit experiment. Before detection, the electron's wave function spreads towards the screen. It assigns probability amplitudes to many possible arrival positions. Some positions have large amplitudes, others have small ones, and a few may have amplitudes that nearly cancel. The wave function therefore contains a distribution of possible detections, yet when the electron reaches the screen, only one mark appears. The detector does not show a faint trace at every possible position. It records one localized event. The next electron produces another single mark, perhaps somewhere else. Quantum mechanics predicts the distribution of these events through Born's rule. The probability of each outcome is obtained from the squared magnitude of the corresponding amplitude. But Born's rule does not explain why one particular possibility becomes the actual result in an individual run. Textbook quantum mechanics introduces a second rule for this moment. During ordinary evolution, the wave function changes continuously according to the Schrödinger equation. During measurement, it is said to undergo projection or collapse. The broad superposition of possible outcomes is replaced by the single state associated with the observed result. The probability of each possible collapse is given by Born's rule. If the electron is detected at one point on the screen, the wave function is updated to a state consistent with that location. All the other possible positions cease to contribute to later predictions for that electron. This rule works extremely well in practice. Physicists use it to calculate atomic transitions, photon detections, particle collisions, and laboratory measurements with extraordinary accuracy. The difficulty is not that collapse produces the wrong predictions. The difficulty is understanding what collapse physically is, when it occurs, and why measurement should be governed by a rule different from every other interaction. A detector is made from atoms. Those atoms are quantum systems. The screen, its electronics, the surrounding air, and the observer's eyes are all composed of particles that should, in principle, follow quantum laws. Why should an electron evolve through a superposition before reaching the detector, while the detector itself is assumed to produce one definite result? John von Neumann examined this difficulty in his formal treatment of quantum measurement. Von Neumann described measurement as an interaction that correlates a system with an apparatus. If the electron can arrive at several positions, the detector should become entangled with those possibilities. One part of the combined state contains the electron arriving at the first location and the detector recording the first result. Another contains the electron arriving elsewhere and the detector recording that alternative. If the Schrödinger equation is applied consistently, the apparatus does not automatically choose one reading. It enters a superposition of correlated records. The same reasoning can be extended further. The detector becomes correlated with a computer. The computer becomes correlated with the light reaching an observer. The observer's brain becomes correlated with the result. This sequence is sometimes called the von Neumann chain. At no obvious point does ordinary unitary evolution identify a natural boundary where the quantum superposition must suddenly become one classical fact. Erwin Schrödinger exposed the absurdity of extending this chain into the macroscopic world through his famous cat thought experiment. A cat is placed in a sealed box with a quantum event, such as the possible decay of a radioactive atom. The decay triggers a mechanism that releases poison. If the atom decays, the cat dies. If it does not, the cat remains alive. Before observation, a simple application of unitary quantum evolution seems to produce an entangled state containing both alternatives, one branch with a living cat and another with a dead cat. Schrödinger did not propose this as a convenient way to keep pets. He designed it to show how strange the quantum formalism becomes when superpositions are extended without limit from microscopic systems to familiar objects. In ordinary experience, a cat is either alive or dead. A detector displays one reading, an electron leaves one mark. The measurement problem asks how that definite outcome emerges from a wave function containing multiple possibilities. Decoherence provides an important part of the answer. When the detector interacts with the electron and its wider environment, the different possible records become entangled with enormous numbers of surrounding degrees of freedom. A detector showing one result scatters photons differently from a detector showing another. Its atoms vibrate differently. Its electrical signals propagate through different circuits. The alternatives rapidly become separate, stable, outcome-like branches. Interference between those branches becomes effectively impossible to observe. For all practical purposes, the detector behaves as though it occupies one ordinary classical state or another. Yet if the universal state continues to evolve unitarily, decoherence does not remove the other branches from the mathematics. It suppresses interference between them and makes each branch locally self-contained. But the complete state may still contain all of them. This is why decoherence alone does not universally solve the measurement problem. It explains why superpositions become unobservable at macroscopic scales. It explains why particular records become stable. It explains why observers within a branch do not notice interference with other branches. It does not by itself explain why one branch alone is experienced as the unique result, unless an interpretation supplies an additional account. Different approaches respond in different ways. Collapse interpretations treat projection as a fundamental rule. Objective collapse theories modify quantum dynamics so that large superpositions physically break down. Many worlds interpretations deny that only one outcome exists, proposing that all decohered branches continue. Bohmian mechanics adds definite particle configurations guided by the wave function. The disagreement exists because the predictions of ordinary experiments are often the same across these interpretations. The measurement problem should also be separated from the claim that consciousness causes collapse. Standard laboratory calculations do not require a human mind to trigger a result. Detectors record events automatically. photographic plates darken, Geiger counters click. Environmental interactions produce decoherence whether anyone is nearby or not. Some historical discussions have assigned consciousness a special role, but this is not a necessary ingredient in routine quantum mechanics, and is not supported simply by the double-slit experiment. The problem is physical and conceptual, not psychological. It concerns the relationship between three claims. The wave function always evolves unitarily. The wave function provides a complete description of physical reality. Measurements produce one definite outcome. Taken together without further explanation, these claims sit in tension. Unitary evolution preserves superpositions. A complete wave function would then contain all correlated outcomes. Yet, experience presents one result. Different interpretations resolve the tension by modifying or rejecting at least one part of that combination. The mystery is therefore not merely that measurement disturbs a delicate electron. The deeper mystery is that quantum theory describes many possible outcomes with exquisite precision, while every actual experiment appears to deliver only one. The interference pattern tells us how possibilities combine. The measurement problem asks how one possibility becomes a fact. Quantum mechanics gives physicists extraordinarily reliable predictions for the double-slit experiment. It predicts where interference fringes will appear. How their spacing depends on the wavelength and geometry of the apparatus, how the pattern fades as path information becomes available, and how individual detections accumulate into a stable probability distribution. The disagreement begins when physicists ask what that successful mathematics describes. Does the wave function represent something physically real? Does a particle possess a definite path before measurement? Does collapse actually occur? Do all possible outcomes survive? Are quantum properties absolute, or do they exist only relative to other systems? Different interpretations offer different answers, while usually reproducing the same familiar experimental predictions. The Copenhagen interpretation is the oldest and most widely recognized family of views. It is associated especially with Niels Bohr, Werner Heisenberg, and Max Born. Although those scientists did not hold one perfectly uniform doctrine, there is no single official Copenhagen manifesto containing one agreed account of reality. The name instead covers several related attitudes developed during the early years of quantum mechanics. A Copenhagen-style account often treats the wave function as a complete tool for predicting measurement outcomes, without requiring a detailed classical picture of what the electron is doing between preparation and detection. The electron is prepared in a quantum state containing coherent amplitudes associated with both slits. Those amplitudes combine to produce the interference pattern. If a path measurement is performed, the experimental conditions change, and one path result becomes definite. Bohr emphasized complementarity. An arrangement that reveals interference cannot simultaneously provide complete path information. The concepts of wave and particle belong to different experimental contexts and cannot be combined into one unrestricted classical description. Heisenberg placed greater emphasis on the mathematical formalism and the limits of assigning definite values to unmeasured properties. Born interpreted the squared magnitude of the wave function as a probability. Copenhagen approaches are often described as saying that measurement collapses the wave function. In practice, that is how many textbooks organize calculations. Before measurement, the wave function contains several possible outcomes. During measurement, one result is selected according to Born's rule. The difficult question is whether collapse is a real physical event or simply an update in the description used by the observer. Different Copenhagen-influenced physicists have answered that question differently. David Bohm offered a radically different picture. In Bohmian mechanics, also called pilot wave theory, the electron possesses an actual position at every moment. It follows one definite trajectory and passes through one slit rather than literally dividing between both. At the same time, the wave function evolves through both available paths. It acts as a guiding structure that influences the electron's motion. The particle's trajectory is shaped by the complete experimental arrangement. Even when the electron passes through one slit, The part of the guiding wave travelling through the other slit affects the later motion. A large collection of electrons prepared with the appropriate initial distribution therefore forms the same interference pattern predicted by ordinary quantum mechanics. When a path detector is added, the guiding wave becomes entangled with the detector, the effective dynamics change, and the interference pattern disappears. Pilot wave theory preserves definite trajectories, but it does not restore ordinary classical physics. The guiding wave is non-local in systems containing entangled particles, and the electron's motion depends on a wave function defined across configuration space rather than merely on local forces acting at one point. The interpretation shows why the double-slit experiment does not strictly prove that no definite path exists. It rules out a simple classical path independent of the rest of the quantum state, but Bohmian mechanics retains a trajectory by adding a guiding wave with distinctly non-classical behaviour. Hugh Everett proposed another response in the 1950s. Everett's relative state formulation, later associated with the many worlds interpretation, removes fundamental collapse entirely. The universal wave function always evolves according to the Schrödinger equation. When an electron reaches the detector, the electron detector, environment and observer become entangled. One branch contains a detection at one position, another contains a detection elsewhere. After decoherence, these branches cease to interfere in any ordinary observable way. Each observer within a branch experiences one definite result, even though the complete wave function retains all outcomes. In this account, the double-slit pattern emerges from interference before the alternatives become irreversibly entangled with the environment. Detection does not select one possibility and destroy the others. It separates the outcomes into effectively independent branches. Many worlds preserves continuous unitary evolution, but it raises difficult questions of its own. Physicists debate what precisely defines a branch, how probability should be understood when every outcome occurs, and whether the interpretation explains Born's rule or assumes part of what it seeks to derive. Objective collapse theories take the opposite approach. Rather than treating collapse as an update or denying it altogether, these theories propose that collapse is a genuine physical process. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber developed one influential model in which quantum states undergo rare, spontaneous localization events. These events occur extremely infrequently for individual microscopic particles, but become overwhelmingly likely for systems containing enormous numbers of particles. An isolated electron can therefore remain in a superposition long enough to interfere, while a macroscopic detector rapidly settles into one definite state. Objective collapse models modify the standard Schrödinger evolution. This makes them more than philosophical reinterpretations because, in principle, they can predict small deviations from ordinary quantum mechanics. Roger Penrose has proposed that gravity may play a role in the collapse of superpositions involving sufficiently different distributions of mass. The exact mechanism remains speculative, but it has motivated experiments designed to test quantum superposition at increasingly large masses. Carlo Rovelli's relational quantum mechanics begins from another direction. It proposes that physical properties do not always exist as absolute values possessed by systems in isolation. Instead, they become definite relative to particular interactions between systems. An electron may have a definite position relative to the detector that records it, while another system that has not interacted with that detector may describe the combined arrangement differently. The wave function is not necessarily a universal object giving an absolute view from nowhere. It encodes relations between physical systems. Applied to the double slit, the electron's path is not treated as one universal fact that must exist independently of every interaction. Particular properties become meaningful and definite when systems interact. Relational quantum mechanics attempts to preserve realism while abandoning the demand for one observer-independent catalogue of all properties. Quantum Bayesianism, commonly called cubism, moves further towards an information-centered interpretation. Christopher Fuchs and Rudiger Schack are among its leading developers. Cubism treats the quantum state as an agent's structured expectations about the consequences of possible actions upon the world. The wave function is not regarded as a literal physical wave spread through space. Born's rule becomes a normative rule connecting an agent's probability assignments. Measurement outcomes are personal experiences for the agent performing the action, although the external world itself is not denied. Within this view, asking which slit the electron truly used before measurement may demand a kind of answer that the wave function was never intended to provide. The quantum state organizes expectations about future experiences rather than describing a hidden microscopic object in complete detail. Critics worry that this makes physical reality too dependent on agents and personal probabilities. Supporters argue that it removes false puzzles created by treating the wave function as an objective material object when its real function is probabilistic. These interpretations disagree profoundly. Copenhagen approaches limit what can meaningfully be said outside measurement contexts. Bohmian mechanics gives the electron a definite trajectory guided by a wave. Many worlds retains every outcome in a branching universal state. Objective collapse theories make one result physically replace the alternatives. Relational quantum mechanics treats properties as relative to interactions. Cubism interprets the wave function through an agent's expectations, yet each must account for the same experimental facts. With coherent paths, interference appears. With reliable path distinguishability, the ordinary fringes disappear. Individual electrons arrive as localized events. The accumulated distribution follows Born's rule. The double-slit experiment therefore places strict constraints on every interpretation, but it does not select one of them on its own. Its mathematics is shared. Its reality is disputed. The experiment broke the simple classical picture, but it did not tell physicists what should replace it. The double-slit experiment did not break physical reality. It broke a particular classical picture of what physical reality was supposed to be. According to that older picture, every object should possess one definite position and follow one continuous path through space. These properties should exist independently of the way the object is examined. A sufficiently careful measurement should merely reveal what was already there. The experiment shows that this picture cannot be applied straightforwardly to quantum systems. When an electron, photon, atom, or molecule reaches a detector, it produces one localized event. One mark appears at one position. The particle does not distribute fractions of its final detection across the entire screen. Yet when two coherent paths remain available, those individual detections accumulate into an interference pattern. The probability of each arrival depends on amplitudes associated with both alternatives. If the paths become distinguishable, the interference weakens or disappears. If the distinction is removed and coherence is preserved, the pattern can return. This is not a vague, philosophical impression. It is a repeatable experimental relationship. Individual quantum systems produce localized detections. Coherent alternatives generate interference. Distinguishable paths suppress that interference. Between the two extremes, fringe visibility changes continuously with the amount of available path information. What fails is the simple assumption that the particle must possess one ordinary, independently measurable route, while the other path remains physically irrelevant. That does not mean all interpretations forbid definite trajectories. Bohmian mechanics retains a particle with an actual position and one path through the apparatus, but it also requires a guiding wave that evolves through both routes and influences the final distribution. The experiment therefore rules out the uncomplicated classical particle, not every possible theory containing trajectories. It also does not prove that human consciousness creates reality. Detectors operate without anyone watching them. Environmental interactions suppress interference without needing a mind to notice the result. A photon, atom, or molecule can become entangled with its surroundings in an empty laboratory. Nor does the experiment show that particles communicate with the future. Delayed choice experiments reveal that a fixed classical history cannot always be assigned independently of the completed measurement arrangement. They do not permit messages to be sent backwards through time or allow an earlier detection to be rewritten. Logic has not stopped working. Physical objects have not been shown to be imaginary. The universe has not become optional. Quantum mechanics follows precise mathematical rules and makes some of the most accurate predictions in science. What has failed is the expectation that those rules must correspond to the familiar categories of tiny particles and ordinary waves. The same behaviour is not limited to light and electrons. Neutrons have produced interference patterns, confirming that electrically neutral particles also possess matter-wave properties. Individual atoms have been placed into coherent path superpositions and recombined. Atom interferometers now use these effects to make exceptionally sensitive measurements of acceleration, rotation, gravity, and time. Interference has also been demonstrated with fullerene molecules. These structures are hollow cages made from carbon atoms, including the famous molecule containing 60 carbon atoms, whose shape resembles a tiny football. Such experiments made it harder to imagine that quantum interference belonged only to isolated elementary particles. Larger organic compounds followed. Researchers have observed matter-wave interference in complex molecules containing hundreds of atoms and masses far beyond those used in the earliest electron experiments. Biological molecules have also entered this territory. Experiments involving substances such as vitamins, amino acid-related compounds, and other biomolecular structures have demonstrated that chemical complexity does not create a sharp boundary beyond which quantum interference suddenly becomes impossible. The central obstacle is not whether an object is alive, biological, metallic, or chemically complicated. The obstacle is maintaining coherence. Larger systems interact more readily with their surroundings. They emit and absorb thermal radiation. They collide with stray gas molecules. Their internal vibrations can become correlated with their motion. Each interaction can reveal partial information about the path and weaken the interference pattern. Marcus Arndt and researchers in Vienna have played a major role in extending matter-wave interferometry towards larger and more complex systems. Their experiments have involved molecules containing hundreds and later thousands of atoms, requiring carefully controlled sources, high vacuum, precise gratings, and close management of thermal radiation and vibration. More recent experiments have pushed the scale further using sodium nanoparticles. These clusters can contain more than 7,000 atoms and have masses exceeding 170,000 unified atomic mass units. Such particles are still extremely small by everyday standards, measuring only a few billionths of a meter across. Yet they are enormous compared with electrons, atoms, and the molecules used in early matter-wave experiments. Their interference provides another test of whether ordinary linear quantum mechanics remains valid as mass and complexity increase. So far, no confirmed boundary has been found, where quantum principles simply stop applying. That does not mean a football, a person, or a planet could easily be sent through a double slit. Their de Broglie wavelengths would be extraordinarily small, and environmental decoherence would occur with overwhelming speed. Creating and recombining distinct paths would be far beyond present experimental control. The underlying principles, however, are not confined to demonstrations designed mainly to puzzle physicists. Electron interference supports electron microscopy, where electron wavelengths allow structures far smaller than those visible through ordinary optical microscopes to be resolved. Atom interferometers serve as precision sensors. They can measure gravitational acceleration, rotations, magnetic fields, and tiny changes in motion. Related devices are being developed for navigation, geophysics, and tests of fundamental physics. Quantum computing relies on preserving coherent superpositions and controlling how amplitudes interfere. A successful computation arranges those amplitudes so that unwanted results tend to cancel, while useful outcomes become more probable. Quantum communication uses superposition, entanglement, measurement, and the impossibility of copying unknown quantum states perfectly. These properties allow new methods of distributing cryptographic keys and linking future quantum networks. Matter wave experiments also search for possible failures of standard quantum mechanics. Objective collapse theories predict that sufficiently large superpositions may break down spontaneously. Other proposals connect loss of coherence with gravity or unknown environmental effects. By increasing the mass, separation, and duration of quantum superpositions, researchers can test whether the familiar equations remain correct or whether a genuine transition eventually appears. The double-slit experiment therefore broke something very specific. It broke the expectation that reality must always contain one ordinary path, one complete classical history, and one set of properties waiting to be uncovered without regard to the measurement conditions. It replaced that picture with quantum states, probability amplitudes, superposition, entanglement, distinguishability, and localized outcomes. The predictions are extraordinarily clear. Quantum mechanics tells us when the pattern will appear. It tells us how the fringes will move, weaken, vanish, and sometimes return. It describes the transition from coherent alternatives to apparently classical records with remarkable precision. What it does not tell physicists unanimously is what the wave function actually is. It may describe a real physical structure, a guiding field, branching realities, relational properties, potential outcomes, or an agent's expectations. Different interpretations place different realities beneath the same experimental pattern. The final mark on the screen is definite. The wave function contained many possible marks. How one experienced outcome relates to those possibilities remains unresolved. The experiment did not prove that reality is unreal. It revealed that reality is far less classical than it first appeared. The double-slit experiment did not break reality itself. It broke the classical picture of reality that had once seemed unavoidable. In that familiar picture, a particle should always follow one definite route through space. It may pass through the first opening or the second, but never require both alternatives to explain where it eventually arrives. Quantum mechanics showed that microscopic phenomena cannot be understood so simply. Thomas Young first used interference to demonstrate the wave behavior of light. Max Planck later introduced discrete energy quanta, and Albert Einstein showed that light transfers energy in localized packets now called photons. Louis de Broglie extended wave behavior to matter, while electron diffraction confirmed that particles could possess measurable wavelengths. The mystery became clearest when electrons were released one at a time. Each electron produced one localized impact on the detector. No individual particle appeared as a broad wave spread across the screen. Yet after many arrivals, the dots formed an interference pattern shaped by coherent contributions associated with both available paths. When the routes remained indistinguishable, the amplitudes reinforced and cancelled. When a detector or environment acquired reliable path information, the fringes faded or disappeared. The important variable was not human awareness. A detector did not need to be watched, understood, or even read. If the path became physically encoded in distinguishable states, the particle became correlated or entangled with the wider system, and ordinary interference was suppressed. Quantum erasers showed that path distinguishability could be removed within carefully selected correlations, revealing complementary interference patterns without deleting the past. Delayed choice experiments showed that a photon could not be understood as privately deciding at the source whether to behave as a classical wave or particle. Decoherence explained how countless interactions with air, radiation, detectors, and internal motion hide quantum interference in the macroscopic world. None of this requires messages travelling backwards through time, consciousness creating matter, or completed events being rewritten. Quantum mechanics instead provides a remarkably successful framework built from wave functions, probability amplitudes, superposition, entanglement, and Born's rule. It predicts where fringes appear, when they vanish, and how individual outcomes accumulate with extraordinary precision. What remains unsettled is the meaning beneath those predictions. The wave function may represent physical reality, information, branching worlds, a guiding structure, relational properties, or incomplete knowledge. Physicists agree on the experimental results far more readily than they agree on what those results say exists. The deepest lesson of the two slits is therefore not that nothing is real. It is that reality is not required to resemble the familiar objects, paths, and properties through which human intuition first learned to understand the world.